Yeah, so we spoke about homophily, right? Anyone remember what is homophily? Okay, yeah. Okay, and then basically we stopped at the point, right? How do we define similarity and familiarity on social networks, right? So now I will speak about what are the various ways we can define similarity especially on Twitter, right? So that's what I will talk about. Um, yeah, I think this we have already gone through, right? So what is homophily, all of that? Yeah. So now on social media platforms, right, there are a lot of features. All of us basically, like, we do a lot of activities. Based on those activities we can figure out what are the dimensions for computing similarity. For example, right, so the way I write, the way you write, may indicate a similarity between two of us, right? And the topics you post versus topics I post, right, is there a similarity in the topics, right? So then if there is similarity in the topics, we may be interested in the same things, right? So the topic based similarity, the style, right, the way you're writing. So then there is a semantic, which is basically based on the content, right? The content you're writing. So is there similarity in the content? So basically, what we've done, right, we have categorized these features into three or four different dimensions, right? So one is the semantic, which is basically the content. The syntactic is your way of writing, right? The stylometric is how you, the style of writing, and the topics which you are posting or writing on the social media platforms, right? So for computing semantic features, how do we compute, right? So Atman spoke about word embeddings, right? I also spoke about word embeddings. So you can embed the content, right? Word embedding is one way. There are multiple ways you can embed the content. So you can embed the content using, you can actually the whole, whatever post I have made so far, you can put them together and make just one embedding out of it, right? Using paragraph embeddings or sentence embedding. There are a lot of different techniques. And so that is one way this is, and once I have is basically a vector, a representation of my content, right? And so once you have representation of your content, you can do cosine similarity to get the similarity between any two user, right? But the trick is getting this content, this representation of content, right? That's where people try different things. Okay. After that, we have again you syntactic features basically sort of capture this the way you write. Do you use lot of emoticons? Do you use lot of hashtags? Right? All of this, right? So you can basically define syntactic similarity, and then there is a stylometric similarities basically your style of writing, right? So how you write. So there is something called authorship attribution. It's basically given a piece of content, right? Can you figure out who has written it, right? So using the style, like, can you figure out? So there is a lot of work actually in this domain where basically given a piece of content or text, um, people try to figure out who the author is, right? So what they do, they basically train a model. So let's say there are these 6 users I am interested in, so I get their writings and I train a model to learn that this is how the first one writes, this is how the second one writes, right? So that is called authorship attribution, right? And then we can also have topic based similarity, which is basically the kind of topics you are posting, right? So now how do we figure out topics? So there are multiple ways again. So one basic standard way has been for long is basically topic modeling using LDA. I'm not sure how many of you heard LDA. Latent discrete topic allocation. It's okay. I think it's not needed, but I'll explain a bit. And so this is, and then the different kind of scores you can get for the topics in the text, right? So this is these are various dimensions we have defined similarity, right? And once you have the encoding of content, right, you can basically compute cosine similarity to figure out similarity between two users, right? Okay. So yeah. So so far we have been treating hate as a vanilla classification, right? Binaries. Is it hateful versus not, right? But like in the morning we discussed that hate is against a minority group, right? So against a protected minority group. So it's against, let's say, it could be hate against a race, a religion, right? So hate is expressed is in these different categories, right? So can we go beyond the binary classification and figure out that these tweets are for this category of hate, these tweets are for this another category of hate, right? So it's going from binary classification to your multi-class classification. Okay, so from 0, 1 binary classification, now we are saying it's just not hate, we are showing which category of hate it belongs to, right? So that is what we are going to do. And then why are we doing all of this is basically we going to see the existence of homophily, right? Is there a homophily in the users who are generating this hateful content, right? So that is the overall goal, the motive we have for defining all of these, right? We want to define similarity because we want to compute homophily. We want to define familiarity because we want to see homophily in the hateful users, right? And then again, it's not, again we want to see homophily at the hateful level, and also can we go one step down, right? One level below, right? Is there a homophily? uh, Homophily varies across the hateful forms or not, right? Is there a, maybe people who are racist, right, writing racist tweets, they are better connected with each other versus the users who are posting communal, right, tweets, right? So there's the kind of analysis we want to do, right, when we do homophilic analysis. So that's why going beyond the binary classification is important, because we want to, what are the implications of this different kind of hateful speech present. Okay, so I think I will, yeah, so it's the same data set, right? So which we have picked, and we used, yeah, to detect the hateful forms, just yeah, one more, we have basically, we do LDA, which is LDA is basically detecting the topics from um, from documents. Let's say you have 10 maybe 100 different documents, right? Document is basically a document with piece of text, right? Is a document, right? So we have 100 different documents, and we want to figure out what are the various topics present in those documents. So that's where we do the LDA based topic modeling, which is actually is off the shelf tool. The LDA is available. Everybody can use it. So this is existing tool which gives you these topics present, and then you have to experiment a little bit what is the right number of topics you want, because sometimes if you are you have to supply how many topics you want, right? So if you put a large number, maybe the topics will get split across, versus if you supply little number, then the topics will get merged. So there's some experimentation needed, but that can be reused, that LDA tool can be used. Okay, so with that okay, so this in this plot, right? So what we see on the X, you have the percentage of hateful tweets. So basically I am picking the users, if let's say one example, okay, so let's say 7, right? So the users whose tweets, at least 7% of his or her tweets are hateful, right? So that's the bucket we have, let's say this is the right. So this, in this basically what we are saying, the users who fall in this bucket, so users, the fraction of their tweets has to be more than 7%. So these are the, at this point represents, right? And then we are basically saying what is the similarity, what is the familiarity, right? So what we want to see, right, for the users who are generating hateful content, is there more similarity and more familiarity, right? What does homophily mean? So you are similar and you are familiar. So here if you see, so basically, so we are looking at the users in different buckets, right? So users whose tweets are, 7% of his or her tweets are hateful. Then what is their familiarity and similarity, versus let's say pick one more point, 20, right? So 20 is this. Now users whose 20% of the tweets are hateful, So what is the similarity and the familiarity? So if you see, the trend is increasing, right? So basically, as the users who are generating more hateful tweet, right, are more similar and more familiar, and these are normalized, right? Say why normalization is needed, because the number of the users in each bucket may be very different, right? So you would like to normalize. So these are the average mean normalized similarity and familiarity, right? So if you see the blue curve, right? So blue is basically edge based familiarity, which is, there's a way to count how the edge based familiarity is basically edge exists or not, right? So that's the plain simple vanilla way to figure out whether there is a familiarity exist or not, right? So that's, and then there are two different ways we have computed similarity here. So glove similarity and the empath based similarity, right? So glove is basically word embedding based similarity. Empath is basically topic based similarity, right? So for both similarity ways, right, just the edge, the familiarity is increasing, right? So this is, so from this plot, right, it's evident that as hatefulness is increasing, right, as a user becoming more and more hateful, the group is becoming actually basically homophilic in a way, right? So homophily is going up as the hatefulness is going up. So which is quite shocking that people who are hateful actually well connected with each other in a way. Yeah. Okay. So and then I think we did, so there's a few more. So basically we tried with the different types of similarity, right? So it's just not one way of similarity, we have different ways of computing similarity. So we have, so if you see all these, the red curves, red plots, right? There is a stylometric similarity, readability, syntactic, topical similarity. But the trend is sort of same for all kind of similarity metrics. Okay. And then yeah, then the few more similarity, right? This again we have the similar trend, and I think, and yeah, this is for two different data sets. I think, yeah, I don't know whether we should be seeing, yeah. So then again I think so now these are the topics. I know there are a lot of not so good words, but then let's, so these are the various different topics we found in the data set, right? And this, and they're not good to see. Let's just skip, yeah. So but then the point is that these various topics, right? We wanted to see what is the similarity and familiarity for each different topic. What we've seen as hate increases, the similarity is going up, familiarity is also going up. But then is this trend different across different topics, different hateful forms, right? So here if you see topics 0, and there are, so basically the blue is the familiarity and red is the similarity, right? And on this bar plot. So for each topic I have put here a similarity and familiarity values from 0 to 1, right? So now there are few topics, right? So topic 0, topic 3, right? They're quite, the similarity and familiarity are both quite high. So and so that means this, the familiarity, this homophily is different across the different hateful forms, right? So maybe these different hateful forms should be treated differently when it comes to counter hate, right? Because counter hate is basically like a counter fake, right? I will not, I'm just a one liner around it, right? So counter hate is, um, there is a hateful message, right? Now in order to counter it, right, you might want to post something which is opposing in nature, right? So counter hate. So what it means that not all the tweets of hateful tweets should be treated same. Tweets from different categories of hate should be treated differently because people have different nature across these hateful forms. Okay, so with that, yeah, this is for a different, one more community, which is okay. I think, yeah, we can go to the next one. Yeah. So now then, okay. So I started with it. There are how do we define similarity? How do we define familiarity? Right. So similarity we have covered. Familiarity in the previous one we said we basically used age exist or not, but that's a very loose definition of familiarity, right? I know you, you know him. Do have some connection with him because I know you, right? And you know him. So just though there is no edge between two of us, but I still know him through you, right? So just edge exists or not is a loose definition of familiarity. So there has been few other approaches, right? Such as common friend between two of us, right? That could be another way to measure familiarity between us, right? We have more common friends, we have stronger familiarity with, right? Or so then, but again, it doesn't capture two hops away, right? It doesn't capture your three hops away. Now, how far? It doesn't capture the whole network picture, right? So that's where we said we should redefine familiarity. And how are we redefine? It's actually the same what we defined in the previous lecture, right? So what did we do in the previous lecture? That we said, how do we represent a user? Sorry. Yeah, so how do we represent a user is basically and the representation through the graph, right? So and we use the GCN or the autoencoder to get the representation of a user. Now what does that representation say? Is basically says that this is how I am connected in the whole network. So if I have to get similarity between me and you, right? I have your representation, I have my representation, right? I can just get cosine similarity to get the familiarity between two of us, right? So now this familiarity will capture my whole connection, my one hop, two hop, whatever, right? So this basically gives me the whole picture of the graph, and then I get this familiarity. So that's what we are saying here is basically do the same thing, get the representation of a user using your graph, right, the social network, and then do the cosine similarity between two users to get the familiarity between two users, right? Okay, no, I think this is okay. Okay, so this is again the same data set, and yeah, so this is what we're saying. Okay, this is the same plot, right? So it's basically now what we're saying that we have defined a new way of capturing familiarity. Does it work better? Who says, right? We need to validate it. So that's how what we're saying that we already know that as hatefulness increases, homophily should increase because similarity is increasing, familiarity is increasing, right? So now in what we're saying, with the new way of defining familiarity, we should see this trend a little bit better, right? So that's what we're saying. So now here on the X we have basically again the percentage of hateful tweets, on Y we have the, this is the bar plot, Y we have the familiarity and the similarity value, right? So that's the red is similarity, blue is familiarity, right? So yeah, so in the top plot, right, the blue is basically edge based similarity. In the below one, there's a mutual friends which I spoke about, a mutual friends count, and there's one more plot where we are using the GCN based, right, the representation based familiarity. So yeah, so basically what we see that as hatefulness is going up, right, we see these two bars coming more together, right. It's not very evident, but then in the, I mean, there are some cases where it's not happening, but see 15, 16, 18, right, where the fraction of tweets is 18%, right, this point, right. This is, yeah, so this is more or less happening as we going up, as the hatefulness is going up. And then we do the same for the topics we have figured out, right? For the topics again we are computing the homophily, for the, and we compute the similarity and the familiarity. Okay, I think, yeah, I think this is a, yep. So with this I would conclude the homophily part. Anything you would like to discuss or ask, can ask now. Otherwise we'll go to the next one.
For example, when we are talking about that as the hateful content of the speech increases, the similarity also increases between users. In calculating that similarity, do we include the hateful part or not? For example,
We take the whole, so like I said, we have different ways of computing similarity. So one way, when we do semantic embedding, we do the whole content, right?
because like if we include the
I understand. What you're saying this, the,
just because the hatefulness is increasing, then similarity will increase automatically if we do include that portion.
So what you're saying, let's a user will not post all the tweets hateful, right? There will be normal tweets, right? That's what you're saying, right? So let's say I'm posting 10 tweets. Out of those 10, only 2 are hateful, rest 8 are not hateful. Now what you're saying, are we including all the content? Yes, yes, we do. Because otherwise it will be biased, right? Because if I do only the hateful part, then it will anyway go up, right? So yeah, yeah, it has to be the whole content. Okay. Anything else? Okay, then I think let's move on to the next part. Okay, I think a lot of people have already spoken about this topic, information diffusion, right, in online social networks. So, given, okay, let me go, yeah. So, what is information diffusion, right? We all know, right, a tweet going viral. So, what is that? Information diffusion, right? So, if I post something, a video going viral, whatever, anything going viral on WhatsApp is a information diffusion, right? So that is, so how, what is information? Basically, information flowing on the network, right? And what makes some information flow faster versus not, right? So there are various factors, right? So what are you posting, right? For why and where, right? There are a lot of these things will matter when information flows in the network. So today, basically, in the context of hateful speech, so I'll talk about a few models, and then we'll connect with hateful speech, right? How those models can be used to predict information is spread or hateful speech spread on the social networks, right? That's what we'll do. Okay, so in general, there are two categories of information diffusion model. One is the explanatory model, which basically explain why this information diffusion has happened. Another is sort of the predictive ones, right? So there's two big categories. So under explanatory models, we have epidemics models, which we discussed in the morning also. I'll also talk a little bit more. And on the predictive ones, we'll talk about the independent cascade and linear threshold, these two models. And then we'll go into the hateful spread modeling. Okay, so with that, yeah, I know all of you are familiar with this, right? What is SI model?
S is susceptible and I is infected.
Yeah, and what is SIS? Sorry? Susceptible. So SI is basically susceptible. If you become infected, then basically that doesn't go back to the susceptible state, right? SIS allows, like this is there are two states, a susceptible and infected. So in SIS, you can go back to the susceptible state. Okay, so but so now basically like he spoke in the morning, right? So there are two state models, and then there are extension of these, right? SI, now we will go to SIR, right? So SIR is basically susceptible, infected, recovered, right? So now then came SIRS models, which are basically again there are basically three states only, but then from recovered to you can again go back to susceptible. Like your coronavirus, right? COVID, right? What does COVID, which category COVID will fall in?
SIRS only. I have seen many people who have got COVID once and they have also
Uh,
recovered.
yeah,
So
so
if you got,
recovered,
you are still susceptible to that disease.
sorry?
Like COVID, if you like once you recover from COVID, then it is still possible that you get it again. So it comes in the SIRS.
Yeah, yes, yeah, you can again, after recovery, you can again become susceptible, yes, yeah. So now these are the disease spreading model, right? Epidemics. But then how does it relate to information? Information is not exactly same as in a disease, right? Disease has certain different characteristic. Information has a certain different characteristic. So there is lot of work went in this field, right? How do we modify these epidemic models to fit in the information diffusion on social networks, right? So there is plenty of work in this domain, and I will discuss a few of them. Okay, so okay, so basically, so they now in when information, right? So you need not get infected. Let's say you got exposed, right? So when somebody, so when I am following someone, right? He or she posts something. I will anyway get on my Twitter feed, right? but I'm exposed to that information, but that doesn't mean I'm infected, right? So that's where people basically introduce one more state which is called exposed. So you're exposed to that information, but you may not get infected, right? So there is a tweet about certain thing, right, about a certain opinion or idea, but you're not interested, right? So if you're not interested, you will not get infected. You will basically expose, that state is exposed, right? And then later on you might get infected or might not, right? So that's why they introduce another state called exposed, which is basically that you have seen the information, but you haven't you are not infected with that information, right? Okay. So, so that so this is one model which was basically a modification of this existing epidemic model to fit in information diffusion, right? So now then there's another which is basically a single layer SCI model, right? So far I think all of these epidemic models, right? There's COVID will spread from one person to another, doesn't matter, right? If you're susceptible, you may get infected. But then there's, I'll get infected with an information if I am interested in, right? So, and I value that information, right? In disease, you don't have an option. You value it or not, you will anyway get infected. But for an information to infect you, it has to have some value for you, right? So that's where these guys introduced, right? So in value of the information when you get infected. So that's the another modification these people proposed. So the SCIR is again sort of similar what I spoke, exposed, right? It's basically contacted, right? So someone has contacted you with that information, but you need not get infected with it. So that is the SCIR, is especially like all the micro blogs, right? Twitter for that matter. Basically you get contacted because someone has published that information, you've seen it, but then you are not really infected, right? So that's another category. And there this the IRSIR, right? This is again basic one more model to set there is an infection recovery, then you have SIR, right? So it basically used in the process like when there is a who is leaving a network or not, right? Churning effect, right? And yeah, so then there's one more I think we can relate it to better, FSIR, right? So SIR is basically sort of your binary, right? You are in that state or not, right? Is basically binary. That is in state or not, right? But fractional SIR is basically says that, see, I get, let's say I'm really popular, I have lot of followers, a lot of information is presented to me, lot of tweets, but then I don't pay attention to each of those tweets. Only a fraction of those tweets might be in interest to me. So human attention is limited, right? We cannot go through all the tweets. So the FSI says that only a fraction of information is important to us, right? And that's why they have this F fractional word, right? So basically while modeling a tweet, I will get infected if a certain fraction of my neighborhood is interested in, right? So this fraction comes into picture. Now then ESI is basically again emotion is important, right? Well, in the piece of text, right, what emotion is present, like I was saying the morning, if it's a sarcastic tweet, people get infected much earlier, they will retweet it further, right? It's a hateful tweet, they retweet it further, right? So that's the emotional, this basically the content part is important. Okay, with that, I think we can go to the influence model. So basically, under this, right, so there are a lot of how do we figure out who are the influential users, right? And if you can figure out who are the influential users, they can actually help in spreading the information. So there are three different ways, right? One is the network based, right, which we have been doing. What are the network ones? Can we use centrality metrics to figure out, right, who are the important users? Structure hole is another network based measure, right? So all of this is, but then they're not, they're very simple, and the accuracy is sort of poor for these models. And then there are another set of which is basically user attributes based, right? So my activity, if I'm really active, I have a lot of followers, people are retweeting my tweets a lot, so maybe I'm an influential user, right? So all these are basically figuring out who are the people who are influential on the in the network, and they can help in the information spread, right? Maybe, yeah. So there are a lot of papers in this field again, but I think let's not go in the detail. I just cover a few. So in the first one, sorry, but in the first one, they basically using the network structure, right? Using the graph, they figure out who are the opinion leaders, right? So that's the first one, and then, uh, yeah, I think I can skip all of them. Community again, I think let's just, yeah. So community is basically again, you know what is a community? Yeah, so in the communities, basically again you can figure out, right? If a community, if I figure out the community who is important in that community is a leader, right? In a way. So okay, yeah, I think let's go into, yeah. Okay, let's go to the predictive models, right? Basically in the predictive model, we saw that this is how the disease spread, right? It's more explanatory, right? But now we'll go to the predictive one, where we'll basically sell based on who are infected already, who is next going to get infected. So independent cascade is sort of the one of the ways, right, to do the who is going to get infected next, right? So so there are certain rules here, right? So which basically works, right? So there is basically what we say, an inactive node V can be activated by active node U at any point of time, right? Let's say all I am here, all my I have 5 neighbors. So all my neighbors, so my neighbors, if I'm inactive, my neighbors will try to activate me, meaning trying to infect me with a certain probability at time t, right? And once if I get infected, I remain infected forever, right? So that's what happens. And then an active node will never interact with same inactive node again. It will not try to, it will only, the chance is only once. If you basically, the node will try only once. If he or she can infect me, they will, only one chance they will get, right? So this is how it works, right? Basically every active node will try to activate the inactive neighbors only once, and once it gets activated, it will remain in that state forever, right? And this kind of models have been used for basically predicting, and they mainly in the product adoption, right? Viral marketing. So let's say I select a few users, and then I want to figure out, right, if I select these users, what who will get activated, right? So those kind of simulations I can do it beforehand. So you can select different subset of people, and you can try to activate. You can do the simulation, figure out who will get activated. But then again, I think there's a lot of these model we can escape. Yeah. So linear threshold is basically slightly different from independent cascade. Here, what we saying? So it's not all the neighbors of mine will try to activate me, right? And they can try again and again. It's not that only once they will try. They can try again and again, and then and if I cross a certain threshold, I become an active node, right? So that's how the linear threshold works, right? Okay, so yeah, I think we don't have to go all of this. We can, yeah. Okay, so far we spoke about how information diffusion works on social network, right? And now we're going to talk about the hate spread modeling, right? How so okay, this is one of the first paper in this field, right? So in this is the same data which we have been using, right? So these guys started with, right? So basically they have a network, right? So and they have a set of users. They wanted to see how these users are placed in the network, right? In the social network. So they earlier everybody, they were of the opinion that the hateful users may be at the periphery of the network rather than in the central part of the network, right? So that is the hypothesis they had, that are they in the periphery of the networks. So that's the first they process they do. And then what they do is, like, if I have this set of users, so they apply this belief propagation. What is belief propagation? Is basically, I have a certain belief, right? You have a certain belief, and both of the belief will go through you to your neighbors, me to my neighbor, and you to your neighbor. And if the belief exceeds a certain value, then your neighbor will also start believing in that. So through this, and so for hateful use, so I am a hateful user, let's say, and someone, so there are 2 3 hateful users now. uh, 3 of them will try to further spread that belief, and then after a certain time it will converge, right? So then basically belief will say that my 3 users were believing head, now maybe few more I started believing head. So belief propagation, so they had this 544 users, if you remember, which were labeled as hateful. Now these users they placed in the network, and they're in the belief propagation to figure out more users who will become hateful. Okay. Now after doing this, so they were basically looking at at the the graph characteristic of these users, right? So they're saying these, if you say there are more, these users are, right, more, right, they are actually central in the retweet network rather than the lone wolf, right? So which is actually quite surprising that time, that wow, these users are very sort of central in the network rather than in the periphery, right? They also looked at these various other things, right? Centrality metrics, right? Betweenness, eigenness, between hateful and normal users, right? And they found that these centrality metrics are also higher for the hateful users. So, and then there were certain other characteristics such as hateful users have more, basically, since your account might get suspended, right, if Twitter figures out. So they create more and more accounts. Their account are more recent. There's one characteristic they found, right? And they have more status, more follows per day. In general, their tweets are basically sort of back to back, shorter intervals in between, right? They will post more often, and maybe the account doesn't last for long. So that's sort of the characteristic these guys figured out. And yeah, and then these users are more negative, they use fewer words, actually, yeah, which is basically surprising, right? They are not really using these hateful words, right? They are basically actually trying to evade, right? They're trying to bypass the rules or the checks, balances the social media platforms have put in place. So they will not use directly the words which are directly associated with the hateful behavior, right? So that is expected, right? These users will not directly use those words. Okay. So now this is a Oh, so this was the previous was this work was basically done using the Twitter dataset, right? So Twitter is actually a moderated platform, right? So that you cannot directly go and post hateful content. So there is a moderation happens, right? There is a Twitter has policies in place which will curb the hateful or offensive content. But then there is another platform called Gab.com. I don't know how many of you are aware of it. No, any of you? No. So gap.com is basically, there is no moderation. You can post anything you wish, right? It's more free. It's just basically whatever you want, you can post. There's no policy there that we want to curb because it says freedom of speech. So freedom of speech, that's why there is no moderation, no policies. So this is the content these guys have analyzed. Now they have again did the same belief propagation. Using belief propagation, they're basically figuring out who are the hateful users, right? So initially, but they have to figure out the initial seed users who are hateful, and then they use the belief propagation to further figure out who are the other hateful users. Okay. So again, sorry. So again, these guys also have the same set of observations actually. So these hateful users are sort of central in the network, right? They are not at the periphery. They are not lone wolf, right? They are actually at the center, right? And and they are basically, so there, and these hateful tweets are hateful posts gets much more attention, right, in terms of reposting, right. Gab also have retweet kind of a thing, which is basically reposting. So they also, and these hateful users are more proactive and cohesive again, they are more similar and familiar with each other, right. And then more influential due to large values of structure. Basically, they again from the graph point of view, they are also central and they are more influential. So with both the studies have concluded the same, right? These hateful users are actually well connected, central in the network. They like post often. Their tweets get more attention, gets far and wide in the network, right? Okay. So now okay. So far basically with this the with these models, right, we have with the current studies, we know the users, the hateful users are basically central in the network, and they don't they tweet often. So we wanted to figure out, like, given a set of users, like in a regular epidemics, right. So given a set of users who are infected, who are hateful, now who are the next set of users they are going to turn into hateful, right. So that's the question we are asking here. Now, I think this all of this can be. Hmm. Okay, so is the same data, right, which we have been using now basically. So we have a initial seed users which we already labeled, right. This is a 544 hateful users which we've labeled initially, and those users we know where they are in the network. Now based on their position, can we further figure out who are the next set of users which who will turn into, who will become hateful, right. That's what. So we using the SPA process, spread and activation. I'm not sure how many of you are familiar with. Anybody familiar with SPA?
Nobody talked about spy.
Nobody talked about SPA yet. Okay. Also, it's the same process, right? So energy here is basic. So see, there also I think you must have talked about seed users, right? The people who churn, right? So here people who churn is basically the hateful users, right? So in the network you have hateful users and they are like your seed users. So in case of telecom network they were churners. Now once they have churned, they will spread energy. Basically I have churned, I'll tell my friend, okay, I'm leaving this network. So and I am leaving versus one more person leaving, that will have an impact on that user to might further leave that network. So it's the same process here. So it's basically I am hateful versus one more person hateful, and you have two friends who are hateful. So they will give some energy to you in the, which is basically transferring their nature to you, right. So you might turn hateful after some time. So that is the same process we have carried here. Is basically people who were initially hateful, right. So we mark them as the initial seed user, and they then basically transfer the energy to the neighbors, right, and that their neighbors to their neighbors, so on, like the way I think Amit must have spoken about this, like, so that's the same process we do, right. And then what we're saying, we do it basically for different topics separately, right, for each topic separately, because mixing topics might be difficult, right, which topic is being spread, right. So hateful topics, it's a hateful topic one, right, which is, let's say, your racist, right. So racist, we are modeling racist hate in a separate way, and another kind of hate. So there are 7 topics, is 7 different simulations will run, right. That's what I want to say. Okay. Okay, so this is and I think there's a lot of yeah, I get. So in this data, right, we basically had a lot of tweets, so we did manual annotation, right, but here we wanted a bigger sort of bigger set of tweets. So we did some, I will talk about, right, we did some classification, and then we do the topic modeling, right. We get the hateful topics, right, and then we basically run this SPA process, which we calling as topical SPA because we are running per topic, and then we basically at the end of the day we get the next set of users which can turn hateful. Okay, and yeah, so and then this basically same process, right. This is we are doing per topic, but then if you want you can also do it the entire like hateful level. So these users who are hateful, they will basically there's then no topic. The basically all the users who are hateful, there are your initial seed users, and then they will further spread energy in the network, right? So this can be done. So now here, so what we have done is, since there is 19 million tweets, so we have used two classifiers, right? So we basically say that the two models which have learned, right? And these models are not, because this data didn't have labels, right? So these models are trained on a separate data which have labels. So there are basically two different way of learning hateful content, and then we do the voting, right? Is, let's say, classifier A is also saying this is hateful, B is also saying this is hateful, then you have more confidence, right? So because this data didn't have labels, otherwise we could have directly trained on the whole data. So then, so what we do, so we train two different classifiers, right? And then using those two classifiers, we get a majority score, and we label this data, right? So, and then I think this is a, now in order to run this SPA process, right, you need two time segments. So this is a time segment 1, and these were your initial seed users. Now what will happen in time segment 2? Who will turn, or who will become churner? Who will churn, or who will become hateful in the next time segment, right? So that's what, so how do we segment, right? So this data, this is basically, I mean, specific to this data, but then you would like to have at least a fraction of users in the first time segment, right? So here if you see, I think basically this data was from January 2017, right? Atman? Yeah, till October 2017, right? So the tweets were from this duration. So now in the first few months there are not many tweets. So that's why we segmented, like based on this September, around the first time period from Jan to September. Rest is the another time segment. Okay, and yeah, so this is how this regular SPA works, right? This is basically iterative process, right? So given a few initial seed users, right, they will activate, they'll pass their energy to the neighbors, and then if the total energy received is above a certain threshold, the node will become active or will become hateful, right? That's what we have done, and yeah, this is the regular SPA process. And basically we were measuring, right? Now we have done the, so how do we measure the accuracy, right? What are the performance metrics? So there are two ways we are doing. One is the precision, right? And one is the another is the Jaccard coefficient, right? So precision is basically saying, right? So I'm saying,
Ratio of the correct one.
yeah, the correct ones, right? Yeah. And this is basically the Jaccard coefficient is this intersection divided the total of them, right? So this is what we do. And yeah, so now then you can actually see, so basically in a SPA model, right, you that there is a threshold, right? So what happens if you vary the threshold, right? So if we based on the threshold, right, so we will, the precision is will change, right? Because you were you selecting the number based on the threshold, and which will depending on higher the threshold you will have the less people, lower threshold you have more people. So that's why, so with the if you see this precision is basically will go down as you increase the threshold, right? Because this as you increasing the threshold, you have less number of people in your, and similar the Jaccard coefficient is also going down, right? And then you can also pick top 10, 20%, 30%, 40% in that one, right? So if you pick more people, is going becoming bigger, right? Yeah, and then this was actually, this is basically done at the whole the entire hateful or not hateful level. Then we repeated it the per topic also. Uh, okay, I think yeah, we can sort of, yeah, we can skip this. I guess this is good enough. I want to go to another one which is sort of, so this work, okay, so yeah, so this work we did together, Atman, Amit and me, right? So basically what we're saying, right? So let's say there is a, so far we're treating hate, right? So with this tweet is hateful or not, right? We have been saying it's a binary. But do you think it should be binary only? Huh? Yeah, I mean, how strong hateful it is, right? So it should be like a sort of scale, right? Should be a continuous value on on certain scale, right? It need not be just hateful or not, right? So that's what we are saying here. So we basically saying toxicity of a tweet, which is basically hatefulness, you can say in a very rough manner, but toxicity of a tweet. And if that, so once you have toxicity, it's no longer a binary thing. It's basically a continuous value on a scale of 0 to 1. So now can we model, let's say I know this is the toxicity at any point of time, right? Let's say I have the whole network. So I know the tweets, let's say time t, these are the tweets in the network. I know their toxicity, right? I know their toxicity, then can I predict in future what will be the toxicity of the network, right? So toxicity again, as I'm saying, is not, we're not saying it's a binary, hate or not, is basically continuous value. Let's say, let me give an example. So let's say Donald Trump posted a tweet where he was using this hashtag called #MAGA, Make America Great Again, right? That time. So yeah, MAGA has been like, and that was used in a lot of negative context, right? Lot of negative emotions. So #MAGA, those are basically hateful tweets most of the time, right? So let's say Donald Trump posts a tweet with #MAGA, a hateful tweet, and now let's imagine there's nothing else in the network, only that one tweet, right? So with that one tweet, there's a certain toxicity in the network, right? Now, since it's coming from Donald Trump, right? People around him will start retweeting that tweet. It will go further in the network, and that will increase the toxicity of the network, right? So far, only Donald Trump was infected with #MAGA, right? Now, lot more people got infected because they're also retweeting the same tweet. So toxicity of the network is going up in a way, right? If you see from that point of view. Okay. So here basically what we're saying, yeah. So what we're saying that can we predict toxicity of network, given less I know what is the toxicity currently, right? Can I predict future toxicity, right? So yeah, so I think this is all fine. Is yeah. So what is toxicity we have defined already. So now here, so we made a hypothesis, right? Can toxicity prediction be done in a forecasting manner? What is forecasting? You guys know time series forecasting? Anyone? Time series, time series forecasting. Let's say your weather data, right? So you have temperature, humidity, all of that, right? So this, what is temperature? You take temperature reading every 1 minute, right? So temperature at time T1, T2, T3, T4, right? That's a time series, right? So now this is a time series, and then what are you doing? Okay, now I want to forecast for my next 1 day, whatever the weather department does, right? So they have the temperature data for, let's say, last 1 week, and based on the temperature data they forecast, let's say, for next 1 day or 2 days, whatever. So that the 1 week data is basically your context data, and this 1 day is your forecast data, right? So this is basically time series forecasting using the context. I'm going to forecast for the next 1 day. So weather department does a lot. In fact, all this sensor data, right, in a plant, right, or in a factory kind of a setup where you have a lot of sensors, they are giving lot of this different, this is humidity or the health of the equipments they are fitted in, right? So that, and then the sensor data, which is basically a time series data, which is being which they use to forecast for further, right? In fact, demand forecasting, right? Let's say Amazon.com, right? So I mean, it knows these are the users every day, like using my website. So based, and then they do forecasting to proactively figure out the demand, the resource, right? So they can proactively do resource allocation, right? Resource optimization, whatever, right? So time series forecasting is a well established approach where using a certain time series data, they basically forecast for next 1 day or a week or whatever, right? So here, so we pose this question to us, right? That can we use time series based forecasting for toxicity prediction, right? So let's say I have the toxicity of the network on day 1, day 2, day 3, day 4, day 5, day 6, right? Now using this, can I predict or forecast for the day 7, right? So this is what we were interested in, right? So can we use this, the context length of days of data, and then use that to forecast the next few days or hours, right? So this is, so that's how we started, and we want to explore this, what does it make sense to do the time series forecasting in the case of toxicity spread, right? So we have okay. Um, so then now okay. So like let's say we see traffic everywhere. So traffic is again, say road segment 1, road segment 2, road segment 3. You have traffic at time T1, T2, T3, right? So and you have this traffic from every road. And then what if, in order to organize traffic better, they do traffic forecasting, right? But then the traffic, they are connected, right? Roads are connected, roads are not independent, right? So if traffic goes on road 1, probably it will impact the another road also, because it is connected, right? So there is a graph underneath, understand? There is a topology. So roads are connected, so roads have these connections. So when you do traffic forecasting, should the topology be considered, right? So similarly here also, when we are doing toxicity forecasting, should we consider the graph also, right? The graph, there is a graph underneath, right? The users are connected, and there is a toxicity which is like basically coming from the tweets, and there is the users who are connected, right? Should we use the graph part of it, right? And so basically this is the question, right, we are asking, right? So the structure, if we do the structure, the graph structure into account, does it aid in the prediction of toxicity better, right? So that's the question, right? Now the another question we wanted to address is basically, can we use this forecasting started with the basic statistical models, then now we have deep learning based sophisticated approach. So can we use simple models versus do we need really deep learning techniques, right? So that's how we started with. Okay. Yeah, this is the same graph which Atman has shown, right? So we have a directed retweet graph, and yeah. So yeah. So there is a tool called Perspective API from Google. So you can basically pass any text there, and it will give you what is the toxicity score, and the toxicity score is between 0 to 1. So we use the Perspective API tool to get the toxicity score for each tweet, and now we have the toxicity for the entire, for all the tweets in the network, right? Okay. So okay, so now the forecast can be done at different level, right? So I can do forecast, toxicity forecast at the entire graph level. So basically, let's say time t1, these are the tweets at time t1. I get the toxicity of all the tweets, and I get sort of average of all the toxicities to get a toxicity score for that time t1, right? At the entire graph level, just one quantity, right? So I get an average, and then I can do this toxicity forecasting for the next time segments, right? So it's basically at the whole graph level in one shot I do. Versus I can also do at a community level, different communities, right? So I can find these communities, and per communities I take toxicity value. Basically, I compute average of the toxicities, and then basically I can do the prediction at the community level versus at a user level. There are different levels, right? Granularity of forecast can vary. Okay, so this tweet basically, yeah. So I think this plot, this is interesting plot, yeah. So what we are saying, so basically with weeks we are measuring what are the tweet count, and what is there are three different things, right? The low toxicity count, medium toxicity, high toxicity. So three different buckets we have divided the tweets, and we are saying, right, which one this is the train to see that, right? So with time, right, if you see with time, so week 01, this is the first week versus this is the 43rd week, right? The low toxicity tweets are also going up. Right? this medium toxicity, I mean, in general, it seems like the network is becoming more toxic because there are tweets which are, even low toxicity tweets are going up, medium toxicity tweets also going up. So in general, network is becoming more toxic. And this is in the this plot also shows, right? If we take the average toxicity of all the tweets at any point in per week, right? So in general, like initially there's, but then in general it goes up, right? And then there is a sudden increase. So this is again shows that in this data especially, right, the toxicity is going up with time. So that's so we know there's a certain trend now. So why did we do all of this? To just figure out, right, can we even use some sort of forecasting approach to basically model the toxicity spread, and this sort of help us that there is a certain trend that may, so there's the you might, which might help you to predict, right? If there's no trend, we cannot do, there's no, prediction is impossible. Okay. Yeah, so this is the overall architecture, right? So basically we are computing like toxicity score, right? And then like I said, so now we can do the prediction of toxicity at different level, at the whole graph level versus different community level versus different user level, right? So we can do at a various granularity of the entities, right? So basically, we create this, we figure out the entities, right? Then we segment, right? You need to create a time series. So per week versus per day, right? So that's the time series construction. So we create toxicity time series, right? And then we have these multiple models for forecasting, and then we see which one works better, right? So that's what is easy to see, right? In case of forecasting, whatever you predict is matching with the actual or not, right? Thus accuracy is very easy. So basically, okay. So yeah, this we have used prospective API to figure this out. Yeah. Okay, so now, so we have three different levels granularity. We are measuring toxicity. One is the entire graph level, right? That's the first one. So if we treat the whole graph as one entity, we compute the average toxicity, which is basically average of all the tweets. That's the level one. Second is we basically saying we don't want to treat the whole graph as one entity. We divide into different groups, and these groups being communities. So we figure out the communities, and then for each community we do the forecast, right? We do the prediction for toxicity. Okay. Third is, can we basically we pick a certain number of influential users, right? Influential users we find based on centrality values, and we pick their neighborhood, right? So let's say I am influential, so all my neighbors becomes one neighborhood, and I want to see how the toxicity in this neighborhood is going up, right? Is basically I want to forecast at the neighborhood level. So these are the three different entities we have defined. Okay. Okay. Now so now okay, so remember we said that we also want to look at the graph underneath graph while forecasting, right? So we basically define a graph between these entities. So so let's say this is one user A, this is another user B. I have for certain friends, this friend is also to this friend, this. So what do you think should be, I mean, yeah, let me ask, what should be, so let's say if I have to connect user, so user A's neighborhood is this one, right? B's neighborhood is this one, okay? So now what do you think let's say if I have to connect A's neighborhood, A is one entity now, right? So basically this is A is, let's say A dash, this is another entity, B is B dash. So if I have to connect these two neighborhoods, what should be the edge weight? Anybody? Number of common neighbors. So you might want to normalize, right? So is based. So yeah. So this is like we are creating a graph between uh, these entities, Similarly, we can also do for the communities, where here basically you can imagine this is one entity, this is another community, this is one community, and the common people are basically the connections between the two, right? So they, okay. Okay, so so um, so now there are various forecasting approaches we have tried, right? So first is basically for each time series we try independently, right? So let's say you have neighborhood 1, right? A is neighborhood. This is like A, B dash. So I have, let's say, forecast time T1. There is a 0 0.1, let's say T2, 0 0.3, so 4 and T3, 0 0.4. Says has some 0 0.2. Okay, so what I'm saying, now I want to forecast for this A dash and B dash, right? So what I'm saying, they are though interconnect. Let's say A and B are connected with each other, but we're ignoring the relationship, right? We're just saying univariate forecasting. I will just forecast based on whatever A is passed. So I want to, let's say, forecast for T5. There's a question mark, right? So I use these three values to forecast for this slot, right? And similarly for B also I use these three the context values to forecast the next one, right? So here what I'm saying, we're not worrying about what is the relationship between these two. We just basically treating them as independent variable and doing the forecast, right? And then and then we sing forecasting with explicit relationship, right? So in the next version, this is the first one we try. The second one is basically saying we're considering this, there's a edge between these two, right? So I want to take that into account. It might so happen, right? Because A and B are connected, so the past values of A, past values of B, both together can help in predicting this one. Okay. Similarly, past values of A and B can help predicting the future of B. And so future of A depends not only on A but also on B. So when we do with explicit relationship, right? So that's, and then the third is basically I I don't know the relationship, but I say okay, like the way deep learning started, right? I don't know what are the relationship, it will automatically infer the relationships, right? I just give the whole multi-way, so I have 10 time series, I will give all of them together as a multivariate time series, and then the model will figure out what are the relationship and then basically do the forecasting taking into account those relationship, right? So uh, that's what we try, the third variant. Okay, so we have done the segmentation per hour, right? So 1 unit of time is basically 1 hour. So we have these many time segments, right? So now, so basically we have and this we have used a low and community detection algorithm to figure out the communities, which is basically your modularity based community detection, and then we use neighborhood entities for to figure out the most influential. We have used PageRank, right? Okay, so now in order to, let's say, neighborhood A and B, I was just these are connected based on the common neighbors between them, right? So there's a weighted undirected edge based on the number of common neighbors, right? And then for communities also we done the same, right? And for neighborhood also I think we have done the same, right? So now this is the basically community to community graph here, right, in this plot. Okay, so now we're here, right? So we've done this, we are going to do the forecasting, right? So we tried these various forecasting approaches, right? So univariate is the first one, which is basically there's a very famous, right, arima based, which is basically moving average based methods to forecast, right, which is looking at the past and the moving average of the past, you figure out the future, right? So that's the moving average based. Then we tried the graph, right, the explicit relationship one, using the spatio-temporal graph convolutional network. So basically in this model, they look at the connections also and the temporal trend, right? So in order to forecast, you have the context length, the basically your temporal, and then the entities are also connected, which is the space part, the spatial part, right? So we use this STGCM. And finally, for the multivariate forecasting is basically, we're not explicitly feeding the relationship, we're basically feeding the entire set of time series is together as basic one big matrix, right? And that is, there are a couple of approaches already in the literature, so we tried. And this is the basic 96 is sort of context of the history, and the forecast length is 48 here. Okay, so now these are the, okay. So what we're saying, so we are measuring mean average error and root mean square. This is the standard metrics to measure forecast, right? So what is the error your forecasting system is committing? So now if you see, right, so for the graph level, so these errors are computed at each level, the whole graph level, community level, and the user level, right? So user neighborhood level. So if you see, so for ARIMA, right, STGCN doesn't make sense in case of graph because just one entity, right? We don't have graph there. And okay, so ARIMA basically, so if you see the basically the error is least in case of this one, right, page TST. Even for community also, this is the list, and for user neighborhood level, this is the list, right? But if you see the trend in general, right, so ARIMA does very well, right? But then if we are adding the graph structure here, if you see STGCN, right, so what we saying, they both are going down, right? So graph is sort of playing a role here, right? So here, so these are all transformer based method, right? There's a huge number of parameters to train, it's not easy. So let's just forget about them, right? We'll talk about them a little bit later, but let's just focus on these two, which are relatively simple, right? ARIMA is very simple, but STGCN is also relatively simple compared to this transformer based models, right? So in this case, right, if you see, right, for when we are adding relationships, right, this community is connected, this neighborhood is connected, we're putting those relationships explicitly, we have an improvement in both. The mean average error is going down, root mean RMS is also going down. So that means, right, the structure does matter, right? So when we forecast, structure matters, and he shows that structure does matter, right? So that has been like for traffic forecasting also. People have tried STGC, and that's how STGC started with traffic data, right? So there also, if you feed the traffic topology, the road topology, the structure matters, and you can do the better for time series forecasting. Okay, so yeah, I think yeah. So so now, okay, so now we're coming back to the transformers, right? Okay, so we know that I don't know how many of you do you know transformers? Not likely. So maybe I can skip this part. Yeah. Okay. Yeah. I think these are just the plot which showing, right? So it's basically the so the true is blue. Basically, these are the toxicity values, right? And the orange one is the predicted one, the forecasted one. How well it is matching with the original one. This plot shows, right? So as we see, it's beautifully matches. Like the page taste is doing so well, right? It's exactly almost whatever the original one, right? And this is for the graph level, even for the community level, right? The second plot, right? So we are doing really well, right? So apart from this period, I think mostly is sort of doing really well, right? So the error is also pretty less, and this plot shows that the error is less, right? So the forecast is actually pretty close to the original values. Okay, the neighborhood level also, right? If you see, though there are in between more peaks, but then in general the yellow, right, is basically close to the real values. Yeah, I think, yeah. yeah, I can conclude with this. So basically, and now why this is useful, because you can use it in multiple cases, right? So on my Twitter account, they can show this is how my neighborhood is, how much toxic my neighborhood currently is, how toxic it will be in the future, right? So all of that can be done. Even Twitter platform itself can use it, right? This is how the toxic currently the network is, how toxic it will turn, right? So you can have all of these. Basically, there are a lot of industry application for this kind of, right, toxicities forecasting. Right? Okay, with this, I think I can conclude. Yeah. Okay. Okay, I'm done. Yeah. Thank you.